And so now we have Mike Hudson from Waterloo, and who is on Zoom.
Can you see everything look good there?
Yeah, we can see.
Behind you, that's nice. Thanks for the opportunity to speak, and thanks especially to Axel and the LensFit team, ShapePipe team at Saclay, and the LensFit team at UBC, because what they've done is a tremendous amount of background work over the last 4 years to really get this data now in a state where we can start to do science, which of course is very exciting. So I'll try to show you a few little bits of science that we've started to do, but really we've only had these catalogs for a few months, and a couple of the early papers were based on preliminary catalogs. So there's a large team, of course, which is growing as the data becomes more complex with multi-band images. So I'll try to give you a sense of what we've done and what we would like to do in the future. So I'll highlight the topics that you see here very briefly. We'll see if I have time to get through all of them. So some of the very early weak lensing science we've done with the data set, and this sort of serves as a validation of the catalogs, is to use them to measure the masses of clusters of galaxies and groups. So Isaac Spitzer, my student, has submitted a paper on this. So from the UNIONS CFIS data, we can calibrate the masses of clusters of galaxies of different richness. This is from this lambda is a red mapper richness parameter. And so we're encouraged that we see good agreement with previous work. And then we can take the same methodology and apply it to galaxy groups, which has been done a lot less. Groups are a bit harder to study because, of course, the weak lensing signal is much weaker, and you need to stack a large number. So in the same paper, we compare the weak lensing masses of groups, going from quite poor groups all the way up to things which are almost clusters of galaxies, versus what you get from the author, in this case Tinker's estimate, using a completely different statistical technique called abundance matching. So this is sort of an indirect way of assigning a mass, and this is a direct measurement. The abundance matching method is cosmology dependent, so you have to assume a cosmology. In particular, you have to assume something about how inhomogeneous the universe is. This is captured by a parameter called S8. We found already an early indication, perhaps, that the data, when we compare it to the lensing masses, prefer a lower value of this S8 parameter. And of course, S8, as many of you know, some other lensing surveys and other methods, peculiar velocities and other measures of cluster abundance, are all pointing towards a lower estimate of S8 in conflict with what you get from extrapolating measurements from the CMB, from Planck, for example, forward to the present day. And that could be an indication of possibly a big problem in cosmology. It's called the S8 tension. So I'll come back to that at the end. Another fun thing that we can do is to measure the shapes of dark matter halos. So, in simulations, when you do an n-body simulation of cold dark matter, you predict that the halos are triaxial. You may be able to see some of this. And of course, that means in projection, they look elliptical. And this is something that we can measure. There have been a few, not very many measurements of this from galaxy lensing. And we've done one of the first, one of the best, I should say, so far. So the key is that you assume that the light that you can see is aligned with the ellipticity of the halo. And then what you do is you stack. In this case, what we've done is stacked many Sloan LRGs, luminous red galaxies, and align them all. And then you measure the quadrupole of the shear around them. So from the little animation you saw in the beginning, that gravitational lensing, if you have a circularly symmetric source, produces a tangential shear. But if you have a source which is no longer circular, then you get a quadrupole component. And so by measuring the quadrupole of the shear, you can figure out the ellipticity of the halo. And so that's what Bailey Robison, who's a student, former student of mine, has done with an early data set from CFIS. We can measure the masses of the LRGs and their density profile. That's a fairly routine thing. And the new thing is to actually measure this quadrupole signal, which is encoded in these diagrams, which I won't explain because it would take up most of my time. But the bottom line is that you get an estimate of the ellipticity of the dark matter halo, where around halo would be 0 in this notation, and we'd measure a highly significant deviation from 0. So that gives you a taste of some of the things that you can do, and this is only from a small subset of the data. In this case, it was about a third of the data without any photometric redshift. So we expect these types of measurements to improve significantly as we continue to collect more data. Another fun thing you can do is measure direct maps, make direct maps of the dark matter. So that's what's shown in the top panel from some, not all of the patches that Axel showed. So a yellowy color is a high density of dark matter above the average. A dark color is a density below the mean. And you can compare that with the distribution of galaxies, which is shown in the bottom panel. And you can see by eye that there's a relatively good agreement on these very, very large scales, right? So we're now looking at hundreds of megaparsecs between the large-scale distribution of dark matter and the large-scale distribution of light. So that's something we're working to quantify better as time goes on. But it gives you a taste of the kind of things that you'll be able to do. We'll be able to accurately measure the relationship between light and mass on large scales, commonly called biasing in the jargon. But then once we have that calibration, that means we can go back and forth between them. But to do that, we have to measure the mass in the first place. So I'll spend a few more minutes on one other topic. Axel was talking about the technical aspects of it, but I'll show you some of his recent work on what we might call anti-lensing. So normally you have an overdense thing like a galaxy, dark matter halo, or a cluster halo, and that produces a tangential shear. But if you have an underdense region, like a giant cosmic void, what happens is instead you get a radial distortion instead of a tangential one. And so there are different ways to explore that. You can convert those distortions into a dark matter map, and you can compare that to the distribution of the light you see in galaxies. So here in this little panel, we've mapped out the distribution of galaxies, where a darker color is an underdensity of galaxies, and Axel has identified underdense regions shown by these faint circles. And then what you can do is look at the dark matter map and stack those, sort of shift and stack the dark matter map at the locations of those underdense regions. And when you do that, you get what's shown in the bottom panel here, which is that dark stuff there indicates that indeed there is a void, or there is an underdensity in these cosmic voids. So these are voids identified by looking at the distribution of light in 2D, so as projected on the sky. A different angle on the same problem is to look at voids that have been identified in 3D from large spectroscopic surveys like the BOSS survey, for example, and its successor, the eBOSS survey. And here, this is one of the places where the advantage of UNIONS is apparent, because the other large lensing surveys that have been done, in particular dark energy survey, don't have these large spectroscopic surveys in the foreground. And so we can do types of science by virtue of the Sloan main survey and the BOSS and the eBOSS, and then very importantly coming up the DESI surveys, There's science with the cross correlation between what you can identify from spectroscopy and what you measure from weak lensing. So this is a measurement still very preliminary from a student, Hunter Martin, who's looking again at this quantity here on the y-axis is proportional to this tangential shear. But instead of being positive, because this is a void, it's actually a negative signal. So it has a negative density. And you can see that the different catalogs both see a signal of this effect, which we're detecting maybe at the 6 or 7 sigma level. So when we publish this, this will be the best detection of voids that's been done to date. So that gives you a taste of some of the very exciting things that we've started working on. There are many, many more, of course, and these will come as the catalogs get bigger, and we can now invest the time on the analysis side of things. So there's a whole range of science that we've started to explore, ranging from galaxies to large-scale structure. We want to understand, you know, the dark matter halo is really the fundamental piece of information that's the hardest to access observationally, but that tells you the link between the stars you see in galaxies and the actual dark matter, the formation of which drives the formation of the galaxies. So it's a critical ingredient. Sorry? 2 minutes. Thank you. It's a critical ingredient, and we've, you know, previous work has started to map out that so-called galaxy dark galaxy halo connection, but there's a lot of work that we can do, in particular taking advantage of this spectroscopic data in the foreground that's unique to UNIONS/CFIS. So we can look at how the link is between the stellar mass and the halo mass as a function of the halo mass itself, the redshift, the environment a galaxy lives in, and then there's interesting topics we can hit, like trying to detect the tidal stripping of dark matter halos that are in satellites as they fall into a group or cluster, as well as looking at exotic objects like the ultra-diffuse galaxies that you just heard about in Rodrigo's presentation. So we don't know what halos those things live in, and this should allow us to get, if we can find enough of them, should allow us to get a mass for the UDG halos. I already showed you masses of clusters of galaxies, and there are different samples coming up from different surveys. Measuring filaments of the cosmic web is a very hard thing to do and really requires photometric redshifts to do that properly. I showed you a little bit of the negative masses of cosmic voids, and then moving into large-scale structure, I showed you some examples of dark matter mass maps, and we can do cross correlations between those maps. I showed you cross correlations between dark matter and galaxies, but you can also do cross correlation with the CMB, thermal Sunyaev, Zeldovich, etc. And then finally, looking into the future, we want to do these things like test general relativity, see whether that works the way it behaves. You remember from your knowledge of GR that, you know, the photon is deflected by twice the amount that you would expect from a non-relativistic Newtonian calculation. We can measure that now on large scales. And perhaps most prominently and most importantly is the measurement of cosmic shear and this parameter S8, which really tells us about the inhomogeneities in the universe and whether we do or do not have a conflict with CMB measurements, for example. That is, you know, that work has to be done extremely carefully, and it will take a little bit longer. And to get the ultimate measurement, we really need photometric redshifts for that. But we can make a start on it with the data that we have. Okay. So, done?
You're done, yeah.
All right. Two slides. They're very short. We're looking forward to the PhotoZs. This will hugely enhance the power of weak lensing. The set of data that has multi-band photometry should grow very quickly. And if you want to know more and you're not already in UNIONS and you want to do some lensing of your own, as Axel said, our catalogs are out. So join us and talk to us, and we're happy to share. Thanks.
Okay. Thank you, Mike. So I think we ran out of time. So just one question from Tracy Webb.
Hi, sorry, Mike. This is Tracy Webb. I just had a question about one of your first slides on measuring the masses of galaxy clusters. Yeah, so I was just curious, on your left-hand plot, the error bars are quite large, although you've got it divided up into 2 bins in redshift. And I wondered if you could just expand on the limitations of measuring or calibrating richness masses out to higher redshift. Is it limited by the lensing, or is it limited by RedMapper and the other surveys?
Yeah, that's a good question. So yeah, these errors, of course, are right now limited by the relatively smaller area that was used in this data set compared to what we have today. So we expect the sample size to roughly triple. Now, going out to higher redshifts from the lensing perspective, it gets hard when you go beyond, I would say, redshift of 0.6, 0.7. And that's because when you get out to very high redshifts, your clusters are behind most of our sources, right? So, as Axel said, the mean redshift of the sources are around 0.65-ish. We may push that up a little tiny amount, but it's going to be of that order. And so the very high redshift clusters that you might be interested in at redshift 1 are unfortunately going to be tough with this source sample. But below lower redshifts would be great.